Okay, we were discussing manual methods of collecting traffic data. We have discussed manual counting, which involved the how to incorporate the breaks, and we have solved the problem with peak hour factor, and so on and so forth. Now we are moving on to the second part of manual studies, which is to do the speed studies manually. And to do the speed studies manually, we have two methods. You can have a distance, and you can collect the time over the distance and do distance upon time to find out the speed. The distance in that sense is called as a trap. The distance used in that study is called as a trap. Okay, so this is one method. Another method is that you have a handheld speed measuring device, and then you collect the speed data using that device. Now you would be wondering why I'm using the device and still calling it a manual, because the device has to be handled manually for each observation. You have to capture the observation yourself by pressing a button or clicking each time. So that's why it's manual. Now, if you are doing it using a stopwatch, you can have two types of errors. One type is called the random error because of manual handling of the stopwatch. You are supposed to start the watch when the car is exactly at your entry point, the start point, and you are supposed to stop it when the car reaches exactly the end. But it is not humanly possible to do it at the exact microsecond. So there will always be some plus or minus error. Okay, maybe you do it 0.5 second earlier, 0.2 second later, and so on and so forth. But in the end, we take the average. Okay, and you are not doing it intentionally, hopefully. So whatever the error you have, okay, sometimes it is plus, sometimes it's minus, because it's random. You are not doing it intentionally. So in the end, when you will take the average, these errors are supposed to cancel out each other. Okay, sometimes you are a bit early, sometimes you are a bit late, so it should cancel out each other. Okay, then you have the other one, which is called as the parallax error. What is the parallax error? It is the error caused due to your inclined line of sight in the observation. Okay, so if you are observing something with an inclined line of sight, error is caused in your observation, which is called as the parallax error. Okay, what do they have to do with the speed study? You can see it over here. So this is the observer, and this is the road, and this is the start point of the trap, the distance. So when he looks at the end point, his line of sight is tilted. Okay, so with this tilted line of sight, he looks at the car and the stop line. Okay, and they look aligned, but you see actually the car has not reached the end point. So this is the parallax error. Okay, what do we do in this case? For this to demonstrate, I have this example. So we have a speed study in which the trap length was 400 feet. The observer was standing 60 feet away from the road at the start point. So this distance is 60 feet. It is away from the road, okay, at the start point. Is aligned with the start point. From this position, he looks at the end point, and this angle is 60. Okay, it could be anything, but for the sake of convenience, it's a book example. We have 60-degree angle and 60 feet length. Okay, so they put a theodolite here and measured the angle, and they found it to be 60 degrees. Okay, so angle is 60 and d1 is also 60. Now this observer, when he thinks that the car has reached the end point, he stops the watch and he sees that the time is 8.3 seconds. To get the speed, I should do distance upon time, but I can only do distance upon time if the distance and time both are matching. If I know the exact time, or if I know the exact distance which is covered by the car in this much time which I have recorded. So in 8.3 seconds, how much distance a car has covered? Okay, it has actually covered this much, d effective. Okay, d I know is a trap line which is 400 feet. I, or the observer, has fixed it, but d effective I don't know. It is because of the parallax. So first of all, I have to find out the d effective. So I will use this right angle triangle. Okay, the observer and the car. So this d1 is 60 feet, this angle is 60 degrees. So if I take tangent of this angle, so tangent is perpendicular upon base. Your base is with the angle and your perpendicular the other side. So tan 60 is perpendicular upon base. So then d effective is this value. Okay, 60 into tangent of 60. 60 feet is the distance d1 and 60 degrees the angle, this angle. Okay, so this distance comes out to be 103.9 feet. Now I can use it to calculate the speed, distance upon time. So 103.9 divided by time, which was recorded to be 8.3 seconds. 8.3 is given in the question. Okay. So the speed comes out to be 12.5 feet per second, and if I convert it into miles per hour, I will divide it by 1.47. So it will come out to be 8.5 miles per hour. Okay, so this is how we convert it. Okay, and now you can see if you increase d1, then the angle will change, and then obviously you have to recalculate it and so on and so forth. You can do something with the angle and play around and see how can I make d effective equal to d. Okay, some common problems in the speed studies. First of all, we need to avoid the vehicles which are going faster, much faster than the others and much slower than the others. Because when you will take them and put them in calculating the average, they will destroy the average. They will shift it towards one side or the other. If you have 10 values where all values are, for example, less than 50, and then there's one value which is 100, that 100 will take the average above 50, but you know the rest of the values are less than 50, so the average is more than 90% of the data, okay, which because of one value. And the same will happen when you have the lowest value. Okay, secondly, when you are doing it near the intersections, then we have a group of vehicles which are passing through the intersections together. Okay, that group is called as a platoon. We have used this term earlier as well. Okay, so if you are dealing with the platoon, then focus on the first vehicle of the platoon, which is actually the leader. That vehicle decides the speed. Okay, so we focus on that. The third mistake is we do not include heavy vehicles into the calculations, okay, or into the speed studies normally. uh, except if you are focusing specifically on heavy vehicles. Only in that case you can include trucks, or maybe you do only trucks or heavy vehicles then. Okay, but we never mix them because there is a lot of difference between them, the speed of cars and trucks. Okay, then we move towards semi-automated studies. In semi-automated studies, we use portable data collection detectors. So something which we can take with us to the field, we put it there, install it, or place it, it collects data, then we bring it back with us. Okay, so this is called as portable data collection equipment. The most commonly used data collection equipment in this regard is pneumatic road tubes. These are very thin road tubes, okay, very thin black colored tubes which you may find laid across the road. Okay, something like this. Okay, so we put some nail or something there to tie the tube, and on the other side we have the counter. Okay, the counter is making the count. Okay, pneumatic road tube is basically does the count when the tires cross over the tube. Okay, and we know the cars have sets of tires, right? Cars and trucks, they have sets of tires. So these sets of tires are called as axles. Okay, now if you know the length of the car and you know the time when the first axle crossed and the second axle crossed, you can do distance upon time now. Distance is the length between the axles and time is the time taken by the two axles. Now the problem is with pneumatic road tubes, we have to calculate the number of vehicles. Number of axles is not our aim. So we have to do a short manual study to calculate the number of vehicles from the number of axles. Okay, so pneumatic road tubes need an additional short manual study. Okay, so how do we use the data of the short manual study? For example, a 24-hour count is done using pneumatic road tubes, which resulted in this count. I know, as I told you, this is the number of axles, not number of vehicles. I have to convert them into number of vehicles. If I divide it by 2, if I say, okay, car has one axle at the front, one at the back, so I divide by 2. Okay, it's very easy, but it's not accurate because all vehicles are not cars, and then we have trucks which have more than 2 axles. So I need to find out the number by which I can divide this and get the number of vehicles. By the way, this count, when it is taken by any detector, it is called as actuation. So actuation is the traffic count done by a detector. Okay, so they did a manual study, a short manual study, and they found that so this study was not done for 24 hours. Okay, it's done for a smaller period. Okay, and they found that they have in that study they have seen vehicles with two axles 157 times, vehicles with three axles 55 times, with four axles 50 times, and so on and so forth. Now, how do I calculate the average number of axles per vehicle? Okay, so first of all, I will calculate the total number of vehicles which have been observed. Okay, so I need number of vehicles. So I will add this column. Number of vehicles, I will add this column. Okay, so I counted the number of vehicles in this column, total number of vehicles observed 303 in the manual study. Okay, and then so this is not the total 24-hour count, this is a short part of this 24-hour. Then for number of axes observed, I have to find out number of axes in 303 vehicles, not the number of axes which I have put here, because this is just a classification. They can be 2 axes, 3 axes, 4 axes, and so on and so forth. I need exactly number of axes observed in these 303 vehicles. Okay, so what I do, 157 vehicles had 2 axes, 55 vehicles had 3 axes, so I am multiplying them, and then I will add all of these together and I get 892. Okay, then I will calculate now axes per vehicle. Okay, so I will take number of axles divided by number of vehicles. Okay, so when I divide these numbers, I get 2.92 axles per vehicle. Okay, so you can see now it's much more than 2. Okay, so a total count of 24 hours was 11,250. So now I'm calculating number of vehicles in 24 hours. Okay, so total count of 24 hours for axis is this much, and I have 2.92 axis per vehicle. Okay, so it will be it will be 3821 approximately, or 22, let's say, vehicles in 1 day. 24 hours is 1 day. Okay, so this is how we can use a pneumatic road tube, depending upon how detailed the count you want. If you are not interested in separating the count for each direction, one pneumatic road tube is enough. If you want separate counts for each direction, then you will have to use one road tube for each direction. If you want to separate the count for each lane, then for each lane you need a road tube. But how will you place it? Because you cannot place the counter in the middle of the road. So if I am doing it for the second lane, I have to take it from the second lane till the end of the road to put the counter on the side. So what will happen for the second lane? I'll get the count of 2 lanes. So I have to subtract this lane to get the count of only the second lane. Okay, and same thing here. You get the count of 3 lanes. So you have to subtract this count to get the count of only the third lane, and so on and so forth. Number of lanes increase, the number of tubes will increase. Then we have automated studies. Automated studies are done with permanent counters. So these are installed permanently. You cannot take them with you after the counting is finished. So they are done for longer times. The studies which are done with permanent detectors, they are also called as ATCs, automatic traffic counts. They are not doing anything. These detectors can be used for data collection. They can also be used for managing traffic on real time. So detector can be, for example, connected with the signal, or connected with the electronic board which shows different speeds to the drivers. Now go at this speed, or the signal timing should be this, and so on and so forth. This is a very good reference for these type of detectors. Okay, you can have a look at them, but it falls under the area of electrical engineering. So civil engineers do not design the detectors. Okay, some of these detectors work on sound. Okay, so they are sound detectors, and they when the vehicle passes, they capture the sound, the noise level, the increase in noise level, and they count how many times the noise level has increased. Then we have opacity detectors, which basically work on image. So they are like cameras. We have a speed cameras. It's the image. It's an opacity detector. So image is captured, and the software captures the data from the image, or it could be a video as well. Then we have geomagnetic detectors, which work on magnetic sensors or magnetometers. So we have one at one end of the road, the other at the other end of the road, and they are the magnetic field between them, very thin, very weak magnetic field to not disturb the flow. And when the car passes it, the field is broken, and the detector counts for how long and how many times the field was broken. The same thing for any other transmitted energy as well. You can have infrared, you can have radar, microwave, ultrasonic. Works on the same principle as geomagnetic. Detector on one side and another one on the other side. A field is created, the field is broken, the count is made. Then we have electromagnetic induction detectors, which are also called as loop detectors. They are placed under the pavement. I called them earlier as point detectors, and they are two, so that's why they are called as the loop, and they are very commonly used near the signals. Their main task is to measure the speed of the vehicle. So when it goes from, I told you there are two, so when it goes from one detector to the other detector, the time is measured, that the car took this much time to go from the first to the second. And in Bahrain they are also used for managing the yellow time of the signal based upon the speed of the car. Then we have vibration detectors. They are again point detectors, and when the car passes you feel some vibration, especially on the bridges. But these detectors are very sensitive, so they can also feel the vibration when it's a normal highway at grade. And again, when the vibration is caused, the observation is made. Then we have a system which is called as VIP, video image processing. I already gave you a hint about this system, a type of opacity detector, but it comprises of the entire system using a camera, a microprocessor, and a software. Okay, so the camera captures the image, the microprocessor will store the data and interpret the image, and the software will convert the data into, or convert the image into traffic data, number of vehicles, speed of vehicles, their path, and so on and so forth. The advantage of this system is that you can capture multiple lanes at a time, okay, without changing or without increasing the number of cameras. One camera can see 3 lanes, 4 lanes, 5 lanes. It can be captured. The challenge is to, first of all, to find the location where the camera can see all the lanes without any distraction, even with moving vehicles. Even if it's a big truck, it will not block the view of the camera. The second problem is the calibration of the image. The camera is taking the image as a set of pixels. Okay, so camera cannot recognize that this is a vehicle and this is a pedestrian, this is a bicycle. You have to train the software to recognize these different things. And the challenge is that the light conditions on the road can change. Okay, so the same thing may look differently in different light conditions, so you have to train the software and the camera to capture the image in different light conditions. So this is one of the challenges. uh, they are saying that these type of systems are now becoming more and more popular. We haven't seen it in Bahrain, but in other countries, according to their claim, they are becoming popular. And there's a video here as well. You can see it later on. Okay, so this is about this system, and they are saying that such system then can be connected with the signal. And I heard it from an industry expert as well, that it will work very well with the signals because it can see in multiple directions and so on and so forth. Okay, these are the practice problems. You can have a look at them, and hopefully you will find it interesting. Okay, and these are practice problems, so do go through them. Okay, they will also help you with the other topics. They will be helpful there as well. So this is it. Thank you.